Okay, this video is the second part in the thermochem review video, and it's the 4 ways to find delta H topic of discussion. And you have a guided note packet that says exactly that. So we have been through all of these before. It's a review. I'm going to try to move quickly. But again, this is the 4 ways to find delta H, which of course is enthalpy or heat. So the first one is using Q equals MC delta T, and a discussion of calorimetry. So calorimetry is basically a study of the heat flow between the system and the surroundings. And we have done several calorimetry experiments, always involving a coffee cup, so to speak. So it is called coffee cup calorimetry. They use coffee cups because they're made of styrofoam and they're good insulators and they prevent heat loss. So that's the idea of calorimetry. And basically you can find delta H for any reaction that you can do in a coffee cup. And of course using Q equals MC delta T. And this is a huge formula in thermochem. So Q of course stands for heat, most of the time measured in joules. M stands for mass, measured in grams. Delta T is the change in temperature, which is calculated by T final minus T initial. And that can be in degrees Celsius or in Kelvin, keeping in mind, and this is a big kind of takeaway, that a change in temperature in Celsius is equal to a change in Kelvin. So there's no need to convert in the thermochem chapter. If you raise something's temperature by 10 degrees Celsius, you also raise it by 10 Kelvin. So there's no need to do a conversion. A delta T can be represented in either Celsius or Kelvin. And then of course we have C, which is the specific heat capacity. Most of the time that's for water. And so C of H2O is 4.18, and that has units of joules per gram degree Celsius. And basically specific heat capacity is defined as the amount of energy needed to raise 1 gram of water by 1 degree Celsius. Okay, or to raise the temperature of 1 gram of water by 1 degree Celsius. So that's what specific heat capacity is. Water has a very high specific heat capacity in terms of other substances, and that's why when you do a calorimetry experiment, your water never gets super hot because it takes a lot of energy to raise the temperature of water. And of course C is different for all substances, so if it were not water for some reason, you'd have to be given that value. So that's the first way to do it, is to apply the formula of MC delta T. So on your paper, there's 2 examples. The first one is really just an MC delta T equation, and the second one is more of a calorimetry experiment. So if you'd like to try to solve these on your own, you can pause this video. Otherwise, I'm going to solve them. All right, so number 1, how much heat is needed to warm 250 grams of water from 22 Celsius to 98 Celsius? How much heat? So Q, I'm looking for Q. I need an M, I need a C, and I need a delta T. And they gave me all 3. 250 grams. It's water, so specific heat is 4.18 joules per gram degree Celsius. And my T final in this case is the 98. And my T initial is the 22. Do my math. All my units cancel except for joules. Round to 2 sig figs. The answer comes out in joules. 79,000. But you know as well as I do that we often work in kilojoules because they're just easier to deal with. Although this answer is not wrong, it's just easier to write 79 instead of 79,000. It's positive, which should tell you that heat had to go in, and that makes perfect sense. Heat has to go in to raise water's temperature. So that was the first application of MC delta T. And then number 2 is more of a calorimetry experiment. So this is a sample of nickel is heated, placed in a coffee cup calorimeter. After the metal cools in the water, it gives you the final temperature. If the specific heat capacity of nickel is given to you right there, what mass of nickel was originally heated, and assume no extra heat was lost. So I'm looking for mass of nickel. If I'm looking for mass of nickel, then I need to rearrange this equation, and I would need Q of the nickel, I would need C of the nickel, and I would need delta T of the nickel. And initially, it seems like you have these pieces until you figure out very quickly that we do not have Q of the nickel. And so this is one of those calorimetry problems where we first must find Q of the water and then switch its sign. So if I'm going to find Q of the water, I need M of the water, C of the water, and delta T of the water. So here I go. 150 grams was your water mass. 4.18 is your specific heat. And let's see. Water started at, nope, just kidding, ended at 25 degrees Celsius. And it started at 23.5. See, this is what I mean. Look at that temperature change. It's so small. And that's because water has such a high specific heat capacity. This came out to be 940.5 joules. So the H2O gained that much energy, which means the nickel lost that much energy. And so here we go up into your formula. Negative 940.5 joules were lost by the nickel. They told me the specific heat of the nickel was this in my problem. And delta T for the nickel. The nickel ended at the same temperature the water did, 25, but it started really hot. Oops. I guess grams are what you want. You do this math, round to, I guess it's 3 sig figs, and we get 28.3 grams of nickel that were used in this experiment. So that's an application of MC delta T and calorimetry. I didn't really find delta H per se, but I was using the idea of Q in that application. So that is the first application of how we can find delta H. So moving along. The second one I have titled Enthalpies of Formation, which is products minus reactants. We call it P minus R. And so first we need to define what a formation reaction is. And a formation reaction is the formation of 1 mole of a substance from its elements in their standard state. And so an example would be the formation of H2O. So forming H2O from its elements, which of course are H2, it's diatomic, plus O2, it's also diatomic. They're both gases. And I would need to balance this, which ends up looking like this. But if you can remember a discussion in formation reactions, this is not a formation reaction. And that's because it doesn't satisfy this stipulation that it must be 1 mole of my product. So I have to divide everything by 2 here. And I end up with this as my formation reaction. And this now, yes, is a formation reaction. Okay. Now, because it's a formation reaction, hold on, let me grab a paper without moving my camera too bad. Oh, sorry, hold on. Okay, let me fix this. Okay, so if you remember this packet, right? So these are formation, heats of formation, okay, or enthalpies of formation. And so because this is a formation reaction, I can go to, oh, and this would be H2O liquid. I can go to H2O liquid and look it up in my chart. And it's under oxygen, and here it is, H2O liquid. And that is the enthalpy of this reaction. And it happens to be negative 285.83 kilojoules. And the units are actually kilojoules per mole. And that makes perfect sense because I have formed 1 mole of H2O. So that's a formation reaction and the accompanying delta H of formation, okay? But from that idea, we know that we can find delta H for any reaction, okay, any reaction at all, not a formation reaction necessarily, for any reaction, using a formula that looks like this. Delta H equals the sum of the enthalpies of formation of my products minus the sum of the enthalpy of formation of my reactants. That's a lot to write. It's a lot to remember. So we call that P minus R. Okay, all coming from, oops, wrong paper, all coming from this packet. So let's do a reaction and let's calculate its delta H so that we can say we did an example. All right, so let's say we have, let's do a combustion. I think I did H2O gas. I think so. Hold on, let me check. Yeah. Okay. So let's say I have this reaction. It's not balanced, so I need to balance it. 3 carbons, 8, 10, so 5. Okay, so there we go. And I want to know delta H. Well, I would hope that you could guess its sign. It better be negative because this is a combustion reaction. But I need to find its value. So delta H, P minus R. So I go to my products, okay, and I have 3 CO2s and 4 H2Os. So I go to my chart and I look up the values for CO2 and H2O. So CO2's value, and I have these written down, so I'm going to do it quickly, is negative 393.5 kilojoules per mole. But I don't have 1 mole of CO2, I have 3. And so what I essentially do is I multiply this by 3 moles, and that cancels out my mole unit. I'm not going to do that for each one and show you the units, but that's what we're essentially doing. So that's my first product, and remember it was the sum of my products, so I'm going to add to that my 4 moles of H2O, which was, as a gas, negative 241.82 kilojoules. Okay, and that whole thing together, that's my P, so to speak, and then I'm going to subtract from that, I'm running out of room, I apologize, my reactants. So my reactants are 1 mole of propane, which is negative 103.85. Notice I don't have to multiply that by anything because it's only 1. And the enthalpy of formation for O2. And if you go to look up O2, you find that it's 0. And you may remember, and of course 5 times 0 is 0, so it doesn't matter. You may remember that the enthalpy of formation of an element or a diatomic is 0. And so I do the math. Being careful not to drop a sign, being careful to remember this is a negative, I mean a subtraction, and when all is said and done, you should get the delta H for this reaction. Notice it's a large negative number, makes sense to us, it's exothermic, it's a combustion reaction. This works for every reaction provided you have the information from the chart, okay? Every reaction you can find delta H this way. Okay, third, probably the one I have to talk the least about because everybody remembers it, is Hess's law. And Hess's law basically says, so it allows us to calculate delta H. It allows the calculation of delta H for a reaction by manipulating reactions to add together to get the wanted reaction. This is a terrible definition, sorry. And then you add the delta H's together. And so Hess's law, we always talk about how it's so easily recognized because it's a series of reactions listed and then their delta H's. It's kind of hard to not know that you're supposed to do Hess's law when you see that. So if you look down below, this is a perfect Hess's law problem. And I'm going to go ahead and erase this so I can have my whole board. And it basically says, what's the delta H for this reaction? Provided I have these other 3 reactions. Okay, so they tell me I have C2H2 plus 5 halves O2, making 2 CO2s and an H2O liquid, I think, and my delta H is negative 1299.6. And then I have a reaction that says carbon plus O2 yields CO2 and the accompanying delta H. And then the third reaction. Oh. Okay, so of course, here's my goal reaction. And I'm trying to manipulate this down here. So if you can remember when we did, I'm going to change my color so it makes it easier to see. If you can remember doing Hess's law, the first thing we talk about is, are your reactants and your products in the right place in the bottom part? So, you know, we see that there's H2 as a reactant, so that's okay. We see that there's C as a reactant and C as a reactant, so that's okay. But my C2H2 needs to be a product and it's a reactant. So this is where I have to take this, this top equation and pick it up and flip it. Okay, and this is, remember, Hess's law gets kind of messy. Oops, that's a liquid. And so I'm just careful that I don't miscopy something because that's very easy to do. And once I'm sure I've copied it correctly, I kind of get rid of it. I could cross it out, you know, I could erase it completely, but I'm going to leave it. And then I need to keep in mind that since I manipulated my reaction, I must manipulate my delta H, which means it's going to be endothermic because I flipped it. So then I start to think about the fact that it looks like my reactants and products are in the right place. Now I have to be concerned with my values, my mole values. So like I need one C2H2 and I have one C2H2, so that's looking promising. And I need one H2 and I have one H2, again promising. Where the issue comes in is this, the 2. I need 2 carbons and I only have 1 carbon. Now I have some carbon, you know, contained in CO2, but that's not carbon. Okay, that's not plain carbon. I need 2. And so the only way I'm going to get 2 carbons is to double this whole reaction. I mean, if you can remember doing Hess's law in Chem 2, you can double reaction. I mean, you can multiply reactions by some number. You can also divide reactions, by some number. So in this case, I've doubled it, which means I need to come over here and double my delta H. I always just leave a note and take care of that later. But now I should be okay. You know, I'm interested in this guy, and this guy. Cross my fingers, everything else should cancel. So I start canceling. Remember, you can cancel if something is the same on the reactant side and the product side. So I see 1 H2O reactant, 1 H2O product, so that's gone. 2 CO2s reactant, 2 CO2s product. And then I start looking, okay, I want this. So somehow these O2s have to cancel. A little hard to see at first, but 2 O2s plus a half O2 is 2.5 O2s. And then as a product, I have 5 halves, which is in fact 2.5. So this cancels with both of these, leaving me with 2 carbons plus H2, making my product. And I careful with my signs, careful with my manipulation of delta H. And when all is said and done, I got 226.8 kilojoules as my answer. It's a positive value. It's endothermic. And so that is Hess's law. So just keep in mind, you can flip reactions, you can multiply reactions, you can divide reactions. But what you do to a reaction, you must also do to delta H. And that's the important part. Again, Hess's law problems are very easy. Oh, that doesn't erase. Are very easy to recognize because of how they look. With that whole group of reactions, nothing quite looks like that, you know, in another problem. So it's very easy to recognize. Whew, okay, and finally, the fourth one, which is the most recent one to us, which is bonds broken minus bonds formed. And so this is a discussion in Lewis structures. This is a discussion that energy is needed to break a bond. Okay, which means that my energy broken is going to be a positive value. And energy is released when bonds form. So the energy of bond formation is always going to be negative value. And so there's a equation that says I can calculate the delta H of a reaction if I take all the bonds broken and subtract that from all the bonds, well, the bond enthalpies, I guess I should say, that were formed. And so that's the second chart, the one I copied from the textbook, that looks like this. It has all your bond enthalpies for single, double, and triple bonds. We'll do one reaction and we'll call this done. So let me clear this board. Let me draw it up here. And we'll go from there. So here's my example. We have CO, that's carbon monoxide. I'm just going to go ahead and draw Lewis structures for you. Plus Cl2. And making, let's see, Cl, C, double bonded O, Cl. Okay. So I have my reaction drawn. Remember, you can't do this unless you have Lewis structures. So this one's nice to you because they gave you the Lewis structures. I always say it's best to make yourself a list. What bonds did I break and what bonds did I form? So I broke a C triple bond O, and I broke a CL single bond. Remember, your broken bonds will be your reactants, your formed bonds will be your products. And who did I form? Well, I formed a CCl bond and a second CCl bond, so two of them. And I formed a C double bond O. Now all I do is look at my numbers and play my math game. So delta H, bonds broken. So to break a carbon-oxygen triple bond is 1072 kilojoules. Added to break a chlorine-chlorine single is 242 kilojoules. Subtracted from breaking two chlorine-carbon singles is 328 kilojoules. And breaking a carbon-oxygen double bond, forming is 799. I do my math. You can check me, but I get this as my delta H. It's negative. This reaction must be exothermic. So those are your four ways to find delta H. MC delta T, enthalpies of formation using P minus R, Hess's law, and then this idea of bonds broken, the enthalpy of bonds broken minus the enthalpy of bonds formed.